Welcome to my talk. I'm Haijun. I'm presenting Nano Stylus, enhancing input on ultra-small displays with a finger-mounted stylus. This work was done during my internship at Autodesk Research with Tovi, Grossman, and George Fitzmaurice. So smartwatches are getting popular and cheap, and even a grad student can afford 3 smartwatches. And these watches are powerful machines. So the one I'm wearing now is a Samsung Gear Live, released in 2014. It has 1.2 gigahertz CPU, 512 megabytes RAM, and 4 gigabytes storage. And these specs are as same as a desktop computer in 2002 with a Pentium 4 processor. And what you can do in 2002 are amazing. You can edit a complex document, make complex drawing in Photoshop, and play games. On the other hand, what you can do now on a smartwatch is just controlling the music, doing basic sketches, or checking the weather or emails. And it's very hard, as well impossible for tasks such as editing a paragraph or sketching. So why is it impossible? It's because watches are small, and these small devices rely on touch as their primary input modality, exacerbating the fat finger problem where a single finger can easily occlude more than half of this display. So one approach to address this issue is to displace the interaction away from the watch face, such as above the watch or to the bezel of the watch. And this approach focuses on easing the basic navigation with less occlusion, and they are perfect for tasks such as music control and email management. However, it's still very hard for editing a paragraph or sketching. So why is it hard? It's because removing the interaction away from the display also negates the most desirable affordance of touch, the direct one-to-one mapping. We present Nano Stylus, a finger-mounted fine-tip stylus that enables fast and accurate pointing on a smartwatch with almost no occlusion and still preserve the directness of touch. So our idea is to instrument a small stylus on the fingertip. And to build this device, there are several form factors we have to consider. First, how big should the nib be? So if you look at a stylus that can work on current capacitive touch screens, you will basically find 2 types of them. A passive stylus, whose nib size is close to the size of the finger, which is exactly what we are trying to avoid, and an active stylus, whose nib size can be as small as 2 millimeter. We set the nib size as 2 millimeter because it causes less occlusion. For the other 2 form factors, nib length and nib position, we explored several possible variations. So we 3D printed a series of cases which can be worn on the end of the index finger, and a small pipe extruded out from different position of the case, which can house pencil refills of different lengths. We then ask participants to wear them to point and write on physical paper to gather feedback from them. So for the nib position, it turns out extruding the nib from the center was preferred by the participants. As they said, the nib is along the projection of my index finger, and I feel my finger is prolonged and sharpened. For the nib length, we found possible effects of it on the performance. Since the human finger has a natural tremor, it is more difficult to control the endpoint for longer nib. However, with longer nib, less effort was needed to move the endpoint from one position to another because we can leverage the angular movement of our finger. Additionally, the longer nib also reduced the occlusion over the writing surface. So given these potential trade-offs between speed, accuracy, and occlusion, we deferred our decision of the nib length and conducted a study to find the optimal length for our prototype. So one important observation we made is that participants tended to hold their thumb on their index finger for stabilization. And this means the form of the Nano Stylus should allow comfortable placement of the thumb on the index finger. So to sum up, the nib should be 2 millimeter, and it should extrude out from the center of the index finger, and the nib length still requires further investigation. So guided by this form factor requirements, we started to build our prototype. So we took an active stylus from the market, which has 2 mm nib size, and we disassemble it to get a circuit board, and we then separate the nib from the circuit board and instrument the tip on our fingertip. And the circuitry and the battery were placed on the wrist. The Nano Stylus is designed in a fashion that we can easily swap nib of different lenses. And using this prototype, we conducted a 2D pointing study with 12 participants to find an optimal lens for the Nano Stylus. So the studies consist of 3 independent variables. First, the width of the target from 1.5 to 3 mm. Second, the distance between the targets from 3 to 12 mm. And third, the length of the nib from 15 to 30 mm. And we analyze the pointing performance based on the movement time and error rate. So this chart shows the error rate for different nib lenses. As we can see, the shorter the nib, the more accurate, with 50 mm being the most accurate. However, for movement time, 50 mm nib is the slowest. So the 50 mm was the most accurate, while 20 mm was slightly faster. This verifies the trade-off between speed and accuracy we foresaw in our exploration. Since the 20 mm nib will also reduce occlusion, we use a lens of 20 mm in our implementation of the Nano Stylus. So having identified a suitable nib lens for the Nano Stylus, we also want to know the performance of it compared to the other pointing techniques on touch devices. So first, we want to compare the Nano Stylus to a normal stylus. As shown in the picture, the Nano Stylus not only differs from the traditional stylus by how it's held, but it also has a longer nib. So to isolate which of these factors might cause a performance difference, we also include a third condition, a handheld stylus that use the same nib length, exactly the same nib as Nano Stylus. And we also want to further investigate the effect of using thumb to stabilize the positioning of the Nano Stylus. And lastly, we compared all the conditions to touch as a baseline. So we conducted a second 2D pointing study, and the task, procedure, and design were identical to the previous one, with the exception of the 5 new input techniques replacing the 4 nib lenses. So for movement time, the Nano Stylus is as fast as a normal stylus. However, Nano Stylus reduced the error rate by 45% compared to a normal stylus, and by 80% compared to the touch. These results show that the performance of Nano Stylus is very promising. It's as fast as a normal stylus, and it reduced the error rate by 45% compared to a normal stylus, and by 80% compared to the traditional touch interaction. Since the Nano Stylus is also being used above the screen, we also wanted to know how much screen area it can occlude. So we conducted an informal occlusion simulation. So as shown in this heat map, Nano Stylus can significantly reduce the occlusion compared to finger and the stylus. So for now, we can conclude that Nano Stylus enables fast and accurate pointing on a smartwatch with less occlusion. And beyond this, we also explored additional sensing technique to add a new flavor to the smartwatch interaction. So remember that we observed that our participants tended to hold the thumb on the index finger for stabilization. And this provides an opportunity for us to explore the gestures that can be performed by the thumb on the index finger. So we attach gesture pad on both sides of Nano Stylus. And the gesture pad consists of 6 independent pins. These pins connected to a capacitive touch sensor, which can sense whether a pin is being touched or not. By doing so, we can detect one-dimensional gesture on each side independently, performed either by the thumb or the middle finger. And these gestures enable additional functionalities of the Nano Stylus. For example, holding gesture provides a second mode of touch input of the Nano Stylus. It can act as a toggle between single selection and multiple selection. And the swiping gesture can be used for adjusting parameters or issuing commands. And while the Nano Stylus is efficient for precise actions, direct touch might still be preferred for less constrained tasks. So the pad of the index finger is covered by the Nano Stylus, but the middle finger can still be used for physical manipulation. As a proof of concept, we discriminate the event from the Nano Stylus or the middle finger based on the data of the smartwatch's acceleration. The forces of the two touch in the direction perpendicular to the screen are different enough to perform the disambiguation. So the high precision capability, coupled with the implemented sensing technique, enable a rich set of applications on a smartwatch. I will now show you a few examples. So in our email application, you can swipe your thumb while hovering to scroll the list to avoid occlusion. You can tap multiple emails while holding your thumb to select multiple items. And you can swipe on the touchpad to apply actions on the selected emails. For example, swipe thumb down to push emails into archive, swipe thumb up to reply an email, swipe middle finger up to forward an email, and swipe middle finger down to delete emails. And Nano Stylus enables fast text input. Tap on the key's input characters. Tapping while holding the thumb input uppercase letters. We also support copy and paste. So tapping on the text while holding the thumb, select the text between the tapping position and the input position. You can then swipe your thumb up to pull up a copy of the text. Screw your middle finger to scroll the document, and swipe your thumb down to place the copy. With Nano Stylus, you can even do sketching on your smartwatch. So you can leverage the high precision of Nano Stylus to select the color you want from a full color palette. To navigate, you can swipe your thumb while hovering to zoom the canvas. Or use your middle finger to pan the canvas. While swiping the thumb while touching the screen, adjust the stroke width. Here are the amazing sketchings that were drawn by our artist, Rubiet, and each of the drawings took him about 15 to 20 minutes to draw. And you can notice that each of these drawings consists of hundreds of strokes with different color and stroke width. And it's obviously very hard to replicate them with your finger on a smartwatch. So this is Nano Stylus. It provides fast and precise touch input. It causes less occlusion, and it supports complex interactive applications. So one of the limitations of our current prototype is that you have to wear complex circuitry and battery on your wrist. However, we believe that a completely passive Nano Stylus can be achieved in the near future. So touchscreen manufacturers has reported that they can support passive stylus as small as 1 millimeter, and the gesture on the Nano Stylus can be detected by sensors embedded in the watch, like Google Project Soli. And these technologies will allow us to build a Nano Stylus with no circuitry at all. And we also hope that Nano Stylus can be integrated with other finger-mounted wearables in a compact form to enable more interactions with smartwatch and other digital devices. And this concludes my talk, and I would like to give special thanks to Rubiet for the great drawings and to Justin for the occlusion simulation. And I'm happy to take questions.
Great, so please just raise your hand if you have a question. I'll start us off. I'm curious if your users, especially the artist who is drawing all those pictures, had any fatigue from holding the watch steady for so long.
Well, so to get a very good control of the drawing, you have, well, there are multiple things you can do to, so one of the artists on, they try to do sketches on Apple Watch, and there are multiple tips that they use to make a very good drawing on Apple Watch. And the same thing happens here, where you have to place your wrist on the table, for stabilization. Well, I didn't hear anything from Ruby yet that he's fatigued or after the drawings. He's quite happy to do that. But yeah, I mean, definitely, it's not a device that's designed for you to use for an hour or 2 hours like desktop computers.
Thank you. Questions? All right, well, I've got another question then, which is, have you considered what it would be like to take those gestures and put them on the side of a stylus, like just a handheld stylus instead of a pen, because that was a pretty interesting technique.
Oh, so yeah, the handheld stylus, I mean, their work have been exploring the gestures on handheld stylus, from Microsoft research, right? So, yeah.